Pardon me. Good afternoon, Fancy Meat Computers. What a way to start a lecture. Wonderful, wonderful, wonderful. Alright, there we go. So, does anybody remember what slide we were on? Thank you. Thank you. Thank you indeed. So, let me just see here. Do we have any announcements today? Nope, not particularly. Let me just check the slide to see where we were. Yep, this is the slide we were on. Wonderful. Cool. Next slide. So. Right. Let's see. Shall we wait a minute or two for the rest of the class to get here? So, do you guys ever have a week where you're not being destroyed with assignments and midterms and all the rest of it? Or is it just like straight annihilation right until Christmas? I forgot that there was an assignments in this class, and I've already forgotten everything that I taught for. Oof. Woof. Nah, straight annihilation until summer. Ay, ay, ay. Well, that's third year for you. Well, fortunately, in this particular case, all of the lectures are online, so if you want to have a refresher about the material that's on the assignment, I would recommend watching the lecture back again. So, we were talking about referencing. So just to quickly recap, when we're talking about referencing, what we're talking about, actually, is assignment. Assignment, as it's generally considered in an imperative language like C or Python, is actually comprised of at least 3 sub-operations, depending on how complicated it gets. We're going to do a very simple version, which only requires the 3. Hoping in person will makes me more focused in lectures next semester. Yeah, it's, you know, I sympathize with that. Although, having given in-person lectures in the past, I can say with a certain amount of certainty that plenty of people sleep through in-person classes, too. You know, the school shouldn't be able to just casually say, that is school for you. That type of justification to mental state abuse is really sad. Not your fault. This school has made it acceptable. Yeah, I guess it's like, I don't know. I remember my third year was particularly hard as well. Like, first year was, you know, pretty frantic. Second year was okay, and then third year I just got hammered. Um, so, you know, I don't know if like hammering you guys in third year is like a thing that's particular to you or your program or your class. I think it might just be like third year students in general get hammered. But yeah, it's it gets a little bit extreme. I think that it has something to do with the fact that the professors don't have to look at your faces. So it's like, you know, oh, we're going to assign a super huge assignment, and then like the professor no longer has the benefit of looking out over the crowd and saying like, oh, three people just, you know, made faces like, you know, probably quitting would be preferable to this. So yeah. This course isn't the problem, but courses like 3SD3 and 3DB3 are stupid and treat the students like they just exist to do school and nothing else and get away with it. Well, you know, two recourses for you. Number one is just, you know, leave a bad review, which is kind of an in-post sort of a thing and won't help you out while it's going on. But, you know, it's also possible that you could, you know, you could collate together, like, how much work you're being given and bring your complaint to the department. But, yeah. Third year plus a worldwide pandemic has just been too much, to be honest. Yeah, I hear you. It's, you know, the number of things that you have to worry about that aren't school has just been increasing exponentially over the last couple of years. Yeah. Apparently 3SD3 has been this way for a long time. Probably won't change unless it gets a new prof. And then that prof will just, you know, go to some other course, you know? Yeah. Oh, so you all have already spoken to the department then. Eh. Yeah. Well, let me put it to you this way. The way that this course was originally construed, when I received it, it would have definitely have been contributing to that burden. The course as it's currently being instantiated, like I believe it is a lot less work this semester than it was last semester, but that work is like more abstract and theoretical. So, you know, yeah. But anyway, I'm trying my best not to. I'm trying my best to sort of balance, you know, not giving you guys too much and like being the straw that breaks the camel's back versus, you know, it is actually important to learn this material, especially, you know, as you go on. Plus, I think it's really interesting material. But I have sent messages to professors, posted publicly in Teams channel, written emails to department heads. Nothing ever changes. Yeah. Yeah. Well, what can I say? You know? Well, at any rate, we're doing a lecture here, so I'm going to do the lecture. And, hang in there, guys. You know? You know, last time I was aware that the, last time something actually, like, changed. The only time I've seen one of these sorts of campaigns to get the course load lightened actually work was, it was last year. It was the first year class, and it was because of the extenuating circumstances due to COVID. But, essentially, the comp sci reps from the MES, I think you guys have, I think the MES representatives are, I think you've got a comp sci rep in there anyway. But anyway, you should have a class rep, right? And, like, you should have a third-year class rep, so make them do their job, you know? Get this person off their butt and have them talk to the department. Like, the problem is one student complaining is one student complaining, right? What you have to do is you have to, like, it sounds kind of terrible, but, like, get together a petition. But, you know, at any rate, I help a lot by extending the deadlines. Yeah. I know. Normally I wouldn't extend this many deadlines, you know? Like, there comes a point when it's like assignment after assignment after assignment where we're extending the deadlines. It's like, just move the due date, you know? Maybe I should just move the due dates, but... yeah. Mark for class rep. What do you think, Mark? You got enough time to be class rep, too? Oh, has your department... jeez. Okay. Well, anyway, so let's talk about programming and junk. I feel for you guys, I really do, and I'm trying to help you out in the ways that I can, but, you know, it's kind of like it's a systemic problem, and I'm a particular solution, you know? I can only try to make this course a little more bearable. But, anyway, so we were talking about, so essentially we're trying to set up how to do assignment using our very formal system. Yeah. Yeah, hang in there, Mark. You know you can delegate to David if things get too much for you, right? David's having a pretty good semester, I think, so. But anyway, so in general, assignment, because it's interaction with memory, we consider that to be an impure effect or a computational effect. Everything that we've done up to this point is a pure effect. So the modifications that the terms make to themselves through evaluation have no effect outside of the term itself. Impure features, you're communicating with something outside of the program, basically. The way that we're going to handle assignment and references and allocation is very similar to the way that C handles pointers, so if you remember that, you'll have an advantage. Yeah. Yeah, that's yeah, it's too bad you can't delegate doing the 3DB assignment to the other TAs for 1MD3, eh? Because that would be academic dishonesty. So, anyway. So, essentially, we're going to be breaking it down into 3 separate and distinct operations: referencing, assignment, and dereferencing. So, referencing also, I use the term allocation more for referencing, because like the implication with, if you call allocation referencing and then retrieval dereferencing, it sort of implies that the retrieval operation is a destruction operation, which it's not. It's just reading the memory state. But anyway, these operations are implicit to varying degrees in various programming languages, but in ML they're all explicit, so we're going to be following the ML model. So, in order to in order to formalize memory interactions, it makes sense to keep these three operations separate and explicit. I think I did this slide, but we will therefore follow the ML model. We will use the expression ref value to denote the allocation of a memory cell. Note that this is an initialization. So note the value that's being provided here. That's a syntactic requirement. So basically we're saying you can't allocate memory unless you have a value to start it off with. So we avoid the problem that you have in C, where you allocate some piece of memory and it's filled with garbage, right? If you just do a straight malloc in C, the memory that it gives you, it doesn't wipe it first, so you just get garbage. And you can read that garbage if you want, but it doesn't mean anything because it's garbage. So initializer is required. This operation creates a reference to a newly allocated memory cell, which must be captured in order to be preserved. We'll talk about that later. So we'll use : for assignment. This denotes the storage of a value in an existing memory cell. And we will use $R to denote retrieval from a memory cell. So, of course, if we have any new additions to our language, we need to talk typing. So, we have 3 new typing rules for reference, dereference, and assignment, or allocation, dereferencing, and assignment. So, when we allocate memory, the referencing operation will return something of type reference to T1, assuming that T1 had type T1. Yeah. Yes. With dereferencing, if T1 has type reference T1, then the type of the dereferenced T1 is the type T1, as you might expect, right? It's like, if this thing is of a reference type, by dereferencing it, we get just the inner type. And for assignment, if T1 has type reference of type T1 and T2 has type T1, then we can say that the assignment operation itself has type unit. Remember, unit is our void type. Assignment doesn't really have a type, so we give it a type void, like a void-like type, so that we can still reason about it. Basically, this is to distinguish it from untypable procedures, right? Like, what we're trying to do is we're trying to build the type system so that as close to all of the correct functionality is encapsulated by the type system as possible. So if you were to, like, just say, oh, assignment is untyped, then what you're doing is you're saying you're putting assignment in the same category as the errors, and we want to separate it. Are we going to have triple references? Ref to a ref to a ref to a T1. Hypothetically possible. Actually, theoretically highly possible, but I'm not going to put you through that for the purposes of this course. No, we're going to keep our examples reasonably simple. We're not going to get into like double or triple pointers or stuff like that. We're really just interested in how can you do these types of memory management operations in a safe way? Because, we have to recognize, as I'm sure all of you recognize, the way that C does it isn't safe at all, or even a little bit safe. C is not a safe language. So we're gonna see if we can build similar mechanisms in a more safe manner. So, for reference creation, it would make sense for the type of ref value to be the type of the value. However, this isn't accurate. Reference doesn't create a value, it creates a reference to a value, right? Therefore, let's add a new type to our calculus. So, to our set of types, we are adding reference to another type. So this allows us to pick a reference out and, basically, this means that we won't have to worry about mixing up our locations with our other types of things in terms of the type system. The specificity adds something. So, just as C pointers are typed references to some other data, type, we set the type of our created reference as a reference to some other type already in our calculus. So we can have a reference to a natural, a reference to a Boolean, a reference to a lambda expression. That's another thing. So that's a thing that's important to realize. When we're talking about values, we're also talking about lambda expressions, right? That is to say, a term with an unapplied lambda at the top level. These are also values, so these are also applicable for storage in our memory unit, right? Anyway, dereference went over his head. My wife really liked that pun. So, the dereferencing operation has very straightforward typing. The type contained within the reference is the type of the dereferenced reference. Bing, bang, boom. Assignment, however, has some interesting subtleties. First, the assignment itself has type unit, which will allow us to perform sequencing. Secondly, note that the term being assigned is constrained via antecedent to be the same type as the type contained by ref. So, we are not permitted to assign something to a memory location if it's not already of the type of that memory location. Nothing goes over my head. Reflexes are too quick. Wah, wah, wah. So, the term being written and the cell being written to must have the same data type, or else the term is untypable. So we consider it a type violation if you were to, for example, try to write an integer into a Boolean spot. You would need a very type-safe language. Like, I'm trying to think of a language in which that's the case. It's certainly not the case in C, and it's certainly not the case in Python. I believe, I'm not familiar enough with Java, but it might be the case in Java that you're not allowed to assign something of an incompatible type without casting it. Like in C, they'll give you a warning, and Python will just do it, right? Maybe somebody in the chat knows. So, here is an example program. We've gone... So it's kind of amazing. What's today? Is it the 10th of November? We've been studying this stuff since the beginning of September, and here's our first real program. Fascinating, right? So, using the above semantics, we are able to construct programs such as the following. So, we create 3 references, store those locations in X, Y, and Z. We assign the value 2 to X. We assign the value 2 to location Y. We assign to the location Z dereferenced X plus dereferenced Y. We then, as the final step, dereference Z, and that yields 4. So there are some interesting subtleties. Number 1, notice that the last operation here isn't an assignment or a memory, it's neither allocation nor assignment, right? If you recall, the way that we defined the sequencing operator, it's always required as the final, the final thing in a chain, in a sequenced chain of operations is required to return something, right? Even if it returns a unit, it returns something, but it's not required to be unit, right? So, so you can dereference you can dereference one of your locations as the final step in the evaluation chain, and that sort of, for our purposes, this will essentially function in the same way as a return statement. So, notice how we are initializing these three variables. The equal sign, rather than the colon equal sign, tells us that we are not assigning the results of ref0 to a location represented by x, for example. The use of equals is the same as expression renaming in pure lambda calculus. So when we defined a lambda expression as add or pred, that's the same mechanism we're using to say that x is equal to this location reference, or this location, right? It's like more of a variable renaming than anything to do with the memory. And it's very important to keep those ideas separate. Cool. So, good so far? So, in the previous section, or in the previous example, also in the previous section, we used variables x, y, and z to store references to some memory storage unit. Let's explore some of the subtleties of our memory system by considering some programs. So, consider the following. So, x is given reference in a reference, so x is a location initialized with 5. Y is renamed to have the same thing as x. X is then assigned 10. If we dereference y, we also get 10. Oh. Daniel asks. Good questions, Daniel. Since x, y, and z point to the same location, wouldn't this assignment conflict? No, these don't point to separate locations. So all this is I'm performing a referencing operation 3 times with the value of 0 as the default value that gets put in memory. As we're going to see, the actual location itself is implicit in all of this. So, you can imagine your memory unit, right? We ask for one variable to be allocated. It gives us location 13. We ask for another variable to be allocated. It gives us location 27. We ask for another variable to be allocated. We are given location 3726. Right. Yeah, value is not a location. It's a value. So ref0 places 0 into a dedicated register. And it comes up with a new one each time. One of our rules that we're going to see once we formalize the semantics of the allocation operation is that sort of in the same way when you're renaming variables or you're relabeling variables during lambda substitution and that whole process, we search for a location that's unused and then give that as the location. So it's a precondition of the allocation that the location that is being given to, for example, y in this case, is not the location that was given to x. That's an antecedent. So equals is both initialize and allocate. No. So ref0 is both initialize and allocate. Equals is take the result of that and store it in a mathematical variable. Yeah, it's different from it's like, I guess you could in theory consider initialization to have an implicit assignment operation embedded inside of it for the initial value. Yeah, but yeah, that's essentially it. So anyway, aliasing. So if we create a reference, give it an initial value of 5, store that location in x, and if we then store the location designated by x in y, modify x, the change shows up in y. This is called aliasing. So note that although we never assign to y, the changes to x are seen when we dereference y. This is because both x and y reference the same memory cell. So if you were to pull out the location, like if you were to do this in C, for example, what you've done is you've duplicated the pointer itself rather than duplicating the entire data structure. So, in order for x and y to reference independent values, we would have to allocate a new memory cell to y. So, aliasing is also something you can do in Python with mutable data structures, and some other things besides, I believe. So, in Python, if you set L equal to the list 1, 2, 3, if you set M equal to L, and then set L at 1 equal to potato, and then view M, you get 1 potato 3. So it's the same process. That's aliasing again. So in Python, this is a well-known noob trap. An inexperienced programmer will think that they are copying the whole data structure when in fact they are only copying a reference to the data structure. This is something that is always a bit of a hang-up for first years. I usually have to spend at least half an hour explaining this. So, programming experts, however, such as ourselves, such as our humble selves, can put aliasing to good use. We can actually pass the results of calculations around our program using aliased memory cells as implicit communication channels. Mark confirms. It is a well-known noob trap. So, consider the following program. If we have C, yeah, it would be good if you can let first years get this in half an hour. Yeah, right? The global variable trap. Oh, yep. Yeah, don't even get me started on global variables. The best thing for a first year to know about global variables is that they don't exist. Actually, the best thing for most programmers is to forget that global variables even exist. So we can use aliasing to our benefit. You can kind of think like, now that we're beginning to talk about these types of real-world things, hopefully in your minds you should be thinking like, okay, so if this is how I would do assignment, how would I do a class? Or if this is how we do an assignment, how would I do a function, right? Like a function in the C sense, where you have like implicit argument, or you have explicit arguments and an explicit return value, you know? How would you do an imperative function as opposed to a functional function, right? So, think about it this way, right? What makes a return value is that the calling function knows that memory location and the called function knows that memory location. The called function, or the function being called, places its end result in that memory cell, and the function which called that function also knows about that memory cell and grabs the data out of it, you know? So that's like, because like normally when you think about aliasing, you think about like these obscure Python like examples, but like you can use this principle to model data transfer between sub-processes of the same program, right? So, consider the following example. Let's say we allocate a memory cell and label it C. I think label it C is how I'm going to pronounce that. I think that's the most clear. So you are storing the reference C in the Lambda definition. Yes, precisely. I think I may have got the exclamation point on the wrong sides of these things. Whoops. Hold on, let me check the textbook. I think that's supposed to be X. Good God. I would like to apologize for the class for not even being able to copy out of the textbook correctly. No, it is supposed to be dereferenced C. Okay. Alright. It's just the exclamation point's on the wrong side. Yeah, it is supposed to be exclamation point C. I accidentally started remembering assembly from second year. Yeah, right? Yeah, sorry guys, it's the same operation. Let me just fix that real quick. Not sure why that necessitates interrobang. Yes. So. Yeah, there we go. So. So we're going to this is going to be an example of an implicit communication channel. So once we have established some memory location and given that to C, we can then use that memory location in subsequent operations, of course. So we have this function, increment C. It takes something of type unit, right? And it allocates, or it assigns to the memory location C the successor of C, and then returns the dereferenced value, right? And the same thing with decrement. So decrement is you assign to the memory location C the predecessor of whatever was in there. That is, you dereference C, you dereference the location, take the value, perform predecessor, put it back, and then you dereference it to show what it is, right? So this also returns the value. Is it because other people asked what is C? Yeah. I think this is called lexical closure. Maybe? Anyway, so if we start C off having the value 0, if we call increment and give it a unit, like just give it the unit value, that yields 1. If we increment again, that yields 2. If we decrement, it goes back to 1, etc., etc. So basically, these two functions are sharing memory, right? So they're able to communicate with each other. We declare two functions, increment C and decrement C, which assign to C either the successor or the predecessor of the current value, and give the current result of C as a result. If we then package increment and decrement as a record, as follows. We haven't done records, but don't worry, we're going to get to them next week. But a record is, you guys hopefully know what a record is. It's a dictionary in Python is basically what a record is. What would the output be if you didn't sequence the output? Well, it would just be it. It would just be that. You would, it would just not print its output, right? I know it's not a print operation, but, like, this thing would not have, like, the current value as a return value, so we'd have to, like, if we wanted to see what it was, we'd have to dereference it explicitly. But, I don't know, that's just the way that this textbook decided to do it. But, yeah. Hash map! Okay. Anyway, so if you take these two things and package them up as a record, this allows you to pass both functions and their shared state around as a unit. In effect, we have constructed a very rudimentary object in the object-oriented sense. Because remember, what is an object in object-oriented? It is an entity that combines some set of persistent data with operations over that data. So, although we have no explicit constructs yet that are like designated for object-oriented programming, you can see we could create them without having, like at this point, once we add this referencing stuff, we don't even need probably to expand our inner language. We could do it all with derived forms, which is cool and interesting. So, yes, in object-oriented programming, an object combines these two elements and allows the programmer to work with the object as a singular entity. Did you like my pun? It's decrement in ink. It's like ink as in increment, but it's like also ink as in incorporated. Anyway, so garbage collection. So now we're going to talk about garbage collection. We talked a lot about memory allocation, but what about memory deallocation? That is to say, when we no longer need the memory, what do we do with it? Right? So, you know, because you could hypothetically see that as being the fourth operation here, right? Allocation, like allocate, store, read, deallocate. That would sort of complete the set, right? Our language intentionally does not contain an explicit deallocation operation. Such operations are not in general type safe. So deallocation, if you have an explicit deallocation operation inside of your programming language, this will very often lead to a lack of type safety, which is why C does it and practically nobody else does it, because C doesn't care. So consider the following scenario. We have process A and process B, right? So A allocates a new memory cell of type natural, right? B then creates an alias to that memory cell, right? If process A then deallocates the memory cell, process B is left with what we call a dangling reference, right? The fact that B has a reference memory to a memory cell which is no longer allocated is precisely the sort of thing that we want to avoid. That is exactly why we want to do this type system, right? So, and consider the following extension to the scenario from the previous slide. Let's say that process C allocates a Boolean memory cell, and the cell that process C is given happens to be the same location as the location that process A deallocated. In theory, the reason that you would want deallocation is because you don't have infinite memory, and you want to be able to reuse locations. So it's very possible that you would end up with a location being given twice to the same program, at least if it was running long enough. So, this becomes a very, very bad problem. So, question, if we allocate something else to that memory cell, will B no longer be a dangling reference? Yes, but the question is, what is it what is it pointing to, right? So, A, there's no guarantee that the deallocated memory cell won't be reused by the same program. And 2, B, if reused, there's no guarantee that the memory cell will receive the same type of value as before. So you can imagine process C allocating it bool rather than natural, right? So now process B has a reference to what it thinks is a natural, but it's actually a bool. This is a clear and obvious violation of the type system, right? Thus, process B thinks it has a reference to a natural memory cell, when in fact the memory cell contains a bool. So this, like, that's a problem, right? That's clearly and obviously a problem. The way that most modern languages solve the dangling reference problem is through a runtime process known as garbage collection. So, Garbage collection requires access to the table of allocated memory cells. The program is periodically paused and checked that each entry in the table of allocated memory cells has at least one live reference to it inside of the program, right? So if you have any, like, this is basically like dangling reference detection, right? Any orphaned memory cells are then deallocated. And generally speaking, it's considered safe to do so. So, if you have a memory cell that no longer has any valid references to it, we generally think of that memory cell as being garbage. The only thing that gives data any meaning is its context. So if you've lost the context of the data, you have also lost the meaning of the data, which means that it's practically impossible to reconstruct anything useful from it. So we throw it away. It's garbage. We delete it. We wipe the memory, or possibly not wipe the memory. At any rate, it's no longer in the table. So generally, it is impossible to reconstruct a reference to a memory cell once that's lost. So not only does the data become meaningless, where to find it in the memory, even if you knew it existed, finding it in your memory when your memory is how many, like, gigabytes? Just almost completely impossible. Deallocation of memory cells to which no references point is generally considered safe. Garbage collection is like sound effects in a video game. It's doing its job if you forget it's even there. But yeah. So any questions about that? So we're not going to be modeling garbage collection too much. I haven't decided what you guys are doing for tutorial next week. Maybe we'll, like, there's some bits in the appendix about how you would go about formalizing garbage collection, but it's possible that we should just move on to bigger and brighter things. With 3 minutes left in the class. Aha! Someone has a question. Speak! I think there's some other approach except the reference counting. Yeah. I love my notes. It's generally safe to kill orphans with the garbage collector. Yes. Yeah, so... Yeah, sure, I can explain orphaned memory cells. So, just to address your comment, I think there are other approaches except the reference counting. Yes, absolutely. Like, what I'm illustrating to you is like a very basic version that they would have probably put together in the 90s. As programming languages have become more sophisticated, so have their garbage collection mechanisms, because it turns out that, oh god, it's probably an NP-complete problem, finding all the dangling references. But, yeah. I would think it would be more to the point, like, during operations which might cause orphans to perform garbage checking at that point. But, you can think of, like, a million different efficiencies or advancements. But this is the general idea, right? You want to find the dangling references and kill them. Not that, yeah. Or you want to find the orphans. So, an orphan is like the opposite of a dangling reference, right? A dangling reference is a reference that exists in the program to a cell that no longer exists, right? An orphan is a memory cell with no existing references in the program, right? So, as the program proceeds, maybe the reference existed in, like, a particular function's namespace, and now that stack frame has been deallocated and the reference is no longer existing, but the process forgot to deallocate this one variable. That undeallocated variable is an orphan because it has no parent. Good. Well, it's 1 minute till the end of class, so we don't really have time to get into the next one. But I do have a meme for you. I hope that'll hold you over till next time. Are there any further questions? For I in range 100 save, make sure it's saved. Yes, very good. If computers were people. So a memory cell which has a value in it, but is not used anywhere, is called an orphan memory cell. Yes, correct. So we can create an orphan memory cell very easily in our current calculus by just executing ref0 or ref anything and just not saving it, right? So if you subtract the equals C, if you just do ref0, that creates a memory location, but it doesn't save the memory location. It also wouldn't be like, it would violate the type safety of the language because this is supposed to be a unit operation, and that returns a location. So you'd have to like apply that as an argument to a lambda that throws out whatever's applied to it and returns unit. But you could do it. You could definitely create a dangling. You could create an orphaned memory cell very easily in our current calculus. Generally speaking, you don't care when you're doing the math version of all of this because we're doing it in math, we don't have any theoretical limitation to the amount of memory cells that we can hold. Unlike a real computer, which definitely has a physical limitation on the number of memory cells it can hold. Cool. Well, if there's nothing further, I think I'm going to log off here. Thank you very much for taking this your favorite class of a very dark and lonely semester. I'm pulling for you guys. Stay positive. Christmas is coming. Yeah. I don't know. I don't really have any further advice. Take her easy, folks.